For Hilbert's 11th problem, he was again looking back, taking something that had been solved and asking, can we generalise this? How much further can we go? And indeed, once more, he was looking to the work of Carl Friedrich Gauss, who 100 years previously had become fascinated by quadratic forms. Quadratic forms are just equations where every variable is appearing in a pair. X squared plus 2xy plus 3y squared plus 10z squared, that's a quadratic form because every variable is paired up, either with itself or with another variable. And Gauss had wanted to know when two ostensibly different quadratic forms, two quadratic forms that have different equations, were actually representing the same thing, when they were equivalent in some sense. And he had managed to show this for the case where the quadratic forms have rational coefficients. What he'd managed to show was that two very different looking equations, for example, x squared plus y squared and 2x squared plus 2xy plus y squared, could represent exactly the same lattice of points. Those two equations are just metrics, so ways of measuring distance, on the same lattice of points, but expressed in different bases, coordinate systems which take you from the origin to each point. It's kind of obvious, or it makes sense when you think about these equations as being metrics, because they each take a pair of variables, an x and a y, and spit out a single number, the distance. And they're showing that because they are operating on the same lattice, they give out the same set of numbers. You put in all of the integers, all of the x's and y's, and you get out the same set of points, the same set of distances. But Hilbert wanted an answer to the much more general question where you're not restricted to only having algebraic coefficients for your quadratic forms. And in this case, this kind of lattice trick doesn't work. But another thing that Gauss had shown was that there's something called the discriminant, which is a property of each quadratic form. You can calculate it by looking at the coefficients of each quadratic form. And when the discriminants of two quadratic forms are the same, you have the same underlying object being represented. And for the more general problem, you still need that discriminant to be the same for two quadratic forms to be equivalent. You also need something called the Hasse invariant to be the same as well. So again, invariants cropping up.